Hello and welcome to the MIT STM Systems Thinking webinar series. My name is Lois Slavin. I'm the Communications Director here at STM, and I will be your host for today. Before I introduce our speaker, Dr. Burak Gozluklu, I'd like to tell you a little bit about STM. STM stands for System Design and Management, which is SDM stands for System Design and Management, which is MIT's master's program for mid-career professionals, offered jointly by the MIT Sloan School of Management and the MIT School of Engineering. SDM provides an education that focuses on integrating the technical, business, and socio-political components of complex challenges by using systems thinking. Graduates earn an MS in engineering and management from MIT. The SDM Systems Thinking webinar series features research conducted by our faculty, alumni, students, and industry partners. The mission of this series is designed to disseminate information on how to apply systems thinking across virtually any domain. Recordings from prior STM webinars can be accessed and viewed on demand at stm.mit.edu. We will be sent a link to the slides and recording of today's webinar in about 1 week, along with the speaker's contact information. Today's webinar is being presented by Dr. Burak Gozluklu, sorry for the pronunciation, who will be speaking on a systems approach to wind energy. And with that, it's all yours.
Thank you, Louis. Today I'll talk about harnessing wind energy. Right now I'm a MIT STM Fellow and a Research Assistant at System Dynamics Group at MIT. Let me start with myself and quickly give my background. I graduated in 2006 in Middle East Technical University with mechanical engineering major and minor in materials. And in 2008, I started working in Turkish aerospace industries, mainly working for Airbus A350 design of A350 aircraft. Our company is the owner of the ailerons, which is shown on the figure, and it's the control surfaces for the wing used to roll the aircraft. So we were able to design, test, develop, and manufacture the prototype. And meanwhile, I pursued a MS degree in mechanical engineering, and I continue working and continue my endeavor in academics together in parallel. In 2010, I started my PhD program, which is motivated by my work at TAI. And in 2013, we have the first flight of A350. And meanwhile, I also helped to other projects, which is Boeing 787 and also Airbus A400M projects too. And in 2014, I graduated with a PhD. And also, in 2015, I decided to switch to business side of engineering. So to do that, I come to STM program at MIT. And afterwards, in 2016, recently, I interned at Tesla Motors in Palo Alto in the program management group for Model 3 cars. And meanwhile, I worked on different projects, such as drone projects, and also worked for MIT Sloan School. Specifically, in MIT Sloan, I founded a club called Systems Thinking Club, and right now I am conducting the president role in the club. So here we embrace students and faculty and the alumni who like to work on systems thinking in businesses and engineering. So we organize seminars and I'm joining conferences, joining 2 competitions. And right now we have more than 170 members. And in School of Engineering side, I worked on development of some scalable drone system, optimization of design, and statistics and machine learning. Right now I'm working in MIT Management School in system dynamics group to model the product development in a different perspectives. And this project will be used in executive education at MIT Sloan. Eventually, it will be a simulator. So for this subject, we started our the project after we win a competition organized by NASA last year. It was a product development and business case competition. So we won the competition with the STM students, with my STM fellows, in the airborne wind energy category. So let's return back to presentation. I like system architecture class at STM. I try to follow the same process. Here, I start with the level 0, which is the top level approach to the problem. So I do with the problem definition, and I go down with the level 1, it is supplying the energy. And level 2, I go to renewable energies, which is solar and wind energy, and then go to wind energy and airborne wind energy at the end. You can think about this as a reversed tree, where the trunk is at the top and the leaves at the bottom. So you can think about a water drop find its way in a natural way to an optimum solution. So I try to follow such an approach today, and we will have some takeaways from each level. So let's start with the problem definition. The problem definition is so simple and so straightforward, actually. It is 1.1 billion people right now, today, in 2017, 1.1 billion people has no access to electricity. It is almost 20% of all population. And the deficit is concentrated in rural areas, especially in sub-Saharan Africa and South Asia, as well as East Asia. So after I see those pictures, I opened the World Bank's map, which shows the annual energy usage, which is provided in terms of kilogram of oil equivalent per capita. And if you can see the link on the below, you can click that and you can see yourself. It shows such a color map. So once I look at it, I see US has a darker color, darker blue, and Africa has white. So it looks like, okay, we can understand. But if you get into details, so let's look at what is the energy consumption. So in the United States, 1% average consumption of oil is 7,000 kilograms. For France, it is almost a half. For France, it is like 3,600, so two people can have the same energy consumption. Then I look at my own country, Turkey. It seems like 4 people can have the same consumption. So far, it is okay. It's based on the development and the industry we can explain. And I just wonder what happens to South Sudan. Now, it just picked one, by the way. I didn't take the minimum or anything. So this is what happens. Especially, I put this animation slightly slower, so to count how many people can have the same, can survive with this same consumption. It is 118 people with the same energy consumption. It is enough for 180 people in South Sudan. So I try to understand this. So what can be the reason, and how can we solve this, and how can we make a better energy distribution? So I'm going to show a system dynamics, very simple system dynamics causal loop diagram. Whatever I show by arrows, it means it increases. And the first one is the cause. So everything starts with fundamentals. It is food, protection, education, and health. So these are the fundamentals human needs. And this creates some energy consumption. And we provide the energy supply. And the difference is the energy satisfied. So the demand of energy is satisfied. So what happens is a prosperity. There is some prosperity satisfied by the supplied energy. So what happens is this. So we start to dream bigger. And this is based on the hierarchy of human needs. Starting from safety and food, people start to self-actualize themselves and try to dream bigger. But there is something called capacity. And it is confined by resources and also the potential of the people specific to those country or those community. And based on the capacity and dream bigger, the self-actualization, people start to work, build, and create. And this creates a growth for the food, protection, and education. But meanwhile, with this loop, there is another aspect of growth, which is employment, job, production, technology, and peace. So this gives a rise to potential. So potential increases, and eventually this loop becomes a reinforcing loop. So this is the development of the community. So the energy consumption increases as we supply energy to those countries. But after a while, of course, this dream shouldn't be a want more. So I don't go to that level, but at least people try to self-actualize. As we give more energy to them, the loop reinforces itself, and there will be a more energy consumption. So this is the typical S-curve, which is bounded by the resources and potential, is the energy consumption versus time. So right now, the dot shows the underdeveloped countries. As you give energy to them, so this consumption increases and increases in time. And developed countries, OECD countries, is almost saturated in that level. There is a still increase, but very slow, gradual. And developing countries are increasing. At least developed countries didn't start that journey. So 50 billion a year right now until 2030 is enough to provide electricity to the whole world. So I mean this. So let's have these people live their potentials and reach their potentials and let them go through this S-curve. Actually, my idea to show these slides at first is, we know that to develop the underdeveloped countries or helping people, we need to make a handshake between the investors and OECD countries with the poor people. So I mean that there is a huge inequality in energy consumption. But a snapshot, today's snapshot of energy consumption or the market in those countries does not reflect the real market. It is just the beginning of the S-curve. There will be a huge demand in future. As I'm going to show in the next section, actually it has been already happening right now. So simply invest to their potentials and provide the energy need in an increasing way. So this is level 0. I only take 2 takeaways from this one. It is outstanding energy and investment potential for developing countries, and the snapshot is not adequate in terms of energy needs right now today. So let's supply the energy. So let's go one level down. This is a graph from U.S. Energy Information Administration. You see the history and projections based on global energy consumption between the non-OECD and OECD countries. As you see here, the OECD countries has almost saturated. There is still an increase, but very gradual one. But the non-OECD countries increasing and increasing because of the loop that I showed you in the last section. So they are going through their S-curve to have more energy need. So they have already dominated the energy need, but it will be much obvious in the future. But there is one thing. So energy means sometimes the CO2, especially with the fossil fuels. So this is a projection that the CO2 emissions share between OECD and non-OECD. It is so obvious that in future and already begun, the majority of CO2 emissions will be coming from non-OECD countries. But hopefully, luckily, the annual clean energy investments has already begun, and the investment for non-OECD countries has already surpassed the OECD countries. If you look at the graph here, the CS here means the climate scope countries. It is 58 emerging nations in Africa, Asia, Caribbean, Middle East, and in Latin America. And as you see here, the non-OECD countries, the CS countries here is a bit more specific. We don't have China here. And it's increasingly, it has an increasing investment. And the OECD has even decreasing one, but slightly increasing, probably after the recent concerns on green energy. So there's a huge potential. Along with the humanitarian side, there is two issues. Number one is global warming, and number two is economy. And beside of supplying the clean energy, we should think about the centralized or electric distribution or on-grid energy. Unfortunately, for most of those countries, decentralized or on-grid solution is not an answer. This picture gives a good understanding of the situation. You can understand why most of those people have no access, or these grids are not possible for them to have their electricity. So that's why most of people are looking for some mobile and off-grid solutions, such as solar panels. Solar panels are quite good at this, as I'm going to mention in the following slides, in terms of cost, in terms of weight, mobility, etc. So investment in off-grid energy is huge. The demand is huge, but only 0.2% of what is necessary is actually supplied. So right now, $23 billion required additional to have the adequate investment in off-grid energy, but unfortunately, it is only 51 million per year. So for this mid-presentation level 1 conclusions, energy investment in non-OECD will dominate the OECD countries, and it has already begun. And CO2 will be a huge problem if the cheap fossil fuels are employed. And off-grid solutions, mobile, easy-to-use green energy solutions, these LETs are important for the future and the current energy supply for those countries. So I take two of them. The green energy solution is required, and off-grid and easy-to-deploy solution are needed. These are the takeaways that we will use in our future journey in this presentation. So let's go to solar and wind energy. Let's get into the renewable. What is happening there? At first, people think the solar energy and the wind energy are competitors. They are competing each other. So are they two friends, like having this arm fight between each other? Is this the case? Actually, it is not. So this is a figure which is hours. The x-axis is hours of day, and y-axis is the non-dimensional output of energy and also availability. And my friend has calculated this for Plymouth, Massachusetts. And as you see, and also as you expect, the sun, the solar power, is active in the day, in the middle of the day. But interestingly, the wind becomes stronger at the night and weaker in the day. So these guys are complementing each other instead of fighting. The supply is complementing each other through the day. And see what happens per year. Yeah, there is a negative correlation between the wind and solar energies. And throughout the year, it is almost the same, actually. This is showing, so in the mid-region is the June, at 160 day, 160 is the June. So you see in summer, we have more solar energy, and in the winter, we have more wind. So these guys also have some negative correlation between solar and wind energy for both day and the year. Actually, if you look at one country, Germany, you can see throughout the year, Germany uses PV more in summer, but wind energy in the winter. So it is, eventually you have a quite constant energy supply around 6 terawatt hours throughout the year by using two technology as a complementary each other in a hybrid way. So yeah, they're actually good friends. So, but let's get into details of cost. The story is a bit different in terms of cost for these two friends. The y-axis here is the installation cost per watt, and x-axis is the energy capacity. It is between 10 megawatts and 10 kilowatts, and it is divided into two. If you look at the red dots, it is the solar power. As you see, there is a scale of economy. As higher the capacity, we have lower the cost. But even in the small capacity, which is a solution, which is a need for off-grid solutions, off-grid electricity, it is quite cheap. It is okay. But if we go to wind energy, it is not the case. Wind energy is quite competitive at higher energy supply, but for a smaller amount, such as less than 10 kilowatts or 100 kilowatts, which means a huge energy supply for people in non-OECD countries, it is not cost competitive. And unfortunately, it probably won't happen in the near future, the cost competition. This shows the cost versus time, and it shows the change of the cost per year. As you see, the solar power is very good at reducing its cost. At each time, it is going down and down, and even below $2 per watt. It probably has reached that level. But onshore wind energy, actually there is no change. It just stays at the $2 per watt. So there is not a big thing happening here. Sorry. So for this mid-presentation level 2 conclusion, I'll take solar and wind energy are compatible, not substitutional. Solar power is getting cheaper every day. On the other hand, conventional onshore wind turbines are expensive and looks like now getting cheaper. And takeaways is solar and wind energies are substitutionary, and low capacity onshore wind turbines are not cost competitive. So let's go to wind energy. So we are in our journey, we are trying to find the problem and try to propose a solution. So in this presentation, I'll show you 3 short crash courses. No worries, it's a short one, and because we will need those equations, very simple equations, in the following slides. So what is wind energy? Actually, the energy in wind is stored as kinetic energy. As we know from high school, it is 1 over 2 m or m over v squared. And so here we take the m as the volume times the density. So if we calculate the volume as a speed times t, it is the x, and times area, which is the sweep area for a wind turbine. So we come out with the power, which is the energy per time. So it is 1 over 2 a times rho times v to the cube. So the maximum harnessable power is something different. So what we can get from this energy is based on so-called Betz capacity factor, which is a theoretical value that we cannot exceed. It is around 60%. And harness power is based on the efficiency factor, which you can do in your design, whether it can be airborne, wind turbine, or whatever. So this is the efficiency factor that we can play with. And it is the total thing that we will consider is the capacity factor for wind turbines, which is 40 to 50%. So far, what we see and intuitively expect is power is proportional to the swept area, air density, and capacity factor. But what is important is this. Power is proportional to the cube of the wind speed. So wind speed cube is very important. So it means betting on the wind speed would have a much bigger effect than combined influence of all other guys here. So wind speed is very important. This is the end. So I said it was short. So this, what happens to wind in terms of altitude? The y-axis here is the height above the ground, and x-axis is right now the air density. As you see, if we go higher and higher and higher, the air density reduces. It's getting thinner and thinner. But what happens to wind? The wind is opposite. So wind increases as you go higher altitudes. So as we know that the wind speed has a cube effect, so the multiplication of those guys is the power density. So power density increases as we go higher in altitude. It means as we go higher, we have more energy. And of course, there are some effects such as the landscape effect. We call it like frictional layer. In city core, you have to go much higher. In open land, you don't need to go higher. And on the onshore, offshore, it is much lower elevations. Yeah, and then conventional wind turbines are around 80 to 100 meters. It is over here. So for wind turbines, the bigger is better. And this is the reason why each year we see bigger and bigger wind turbines. And if you look at the one which is shown on the right, it is the 7.5 megawatts, and compared to Empire State Building. It's quite big, it's huge. And as I mentioned before, the scale of economics in wind turbines, it's very important. So you are reducing the cost as you increase the size, but they have some problems as I'm going to mention. So in terms of design optimization course, for all-wheel direct course here, I would like to touch to. So we have objective function. It is increasing maximizing the power, and the power equation is this, and don't consider the efficiency right now. So it means the maximization of sweep area and maximization of altitude. It means maximization of wind speed. So we know that the wind speed increases at higher altitudes, and let's put our ground and put a smaller wind turbine and the lower altitude. So to optimize it, I go higher with a bigger wind turbine, and I go higher with a bigger wind turbine. And of course, A3 is bigger than A2 and A1, and altitudes are increased. So higher altitudes, and it means A3 has the highest wind potential, has the highest wind speed. So it looks like I'm going pretty well in terms of maximizing the power, like this. But there is one thing here that I would like to mention, and it is the power, it is the force, wind force. So wind force, the force that exerted to the wind turbine is also increased here. And it is almost the same effect like the power. So for A3, we have a much huge force pushing backwards the wind turbine. For F2, it is smaller. For F1, it is much smaller. So of course, we have to put those guys on the air. So I put some towers like that. So we have to make a small crash course again to understand what's going to happen in the next slides. So this is the beam under banding load. In banding loads, we call on the basement we call moment, which resists the load at the tip. It is proportional to the force times the length. You have the higher force, you have a higher moment, you have a higher length, you have a higher moment. So stress, which happens on the base and which happens to lead to failure of the whole system, is proportional to the moment. And the stress is, for a circular one, is F times L over a geometry, somehow a geometry, and it is the cross-section of the geometry. So the takeaways from this course is this: the stress to windstand is proportional to the F and also proportional to the L, which is the length of the tower of the beam. And I don't even mention about the vibration issues, which has a much higher effect in terms of a slender beam carrying a payload at the top, which is a wind turbine blades. The situation is much severe here, but anyways, let's skip to that point. So, yeah, so this was the slide that I left. So what happens is this. After this course, I think we learned that we have to increase the thickness, the size of the tower to sustain the loads and to have the adequate stiffness for the vibration issues, especially having a rotary system on the top of a tower. I mean, the turbines are rotating, so they are creating an excitation, harmonic excitation to the whole turbine. So you have to increase the size in an increasing way. So at the end, you have a solution like that. And here, this is a composite material mold. Probably seems like the glass fiber composite material. And the transportation, of course. Transportation has a big effect. So you're carrying hundreds of meters of blades to the deployment area. And also the construction and installation has a very huge effect based on the size, on the top of the weight and increasing the thicknesses and the tower, etc. So why it happens? Actually, again, another S curve. This is our second S curve in this presentation. It is simply the wind turbine technology has almost saturated technology achievement so far. It was shocking to me once I realized that the wind turbines was first used in AD 500, thousands of years ago, in Iran, and in the 19th century, in 20th century. So there is a development, but the solution is almost always be the same. Right now, the biggest introduction in terms of technology contribution is the materials, is the lightweight materials. Right now it is the carbon fiber reinforced composite materials. In future it can be a different lighter materials. But still it is right now a strength of materials problem instead of a power or energy supply problem. And maybe some energy conversion and also some gearbox, but mainly the size is the issue, so it means the weight. So the material technology is the driver here. So the presentation conclusions is conventional wind turbines are only cost competitive at high scale power production, very good at it, economics of scale. Unfortunately, because of the size and the weight, which is unavoidable definitely, is making them not mobile, not effective for off-grid applications such as for developing worlds. It is so hard to carry huge wind turbines. And it is not modular, transportation is a problem. And architecture is not suitable for reaching high altitude, high speed winds. So it looks like reaching to the clouds with a ladder. So it is much convenient to drop the ladder. So for this level 3, I take only 2 of them. It's architectural of conventional wind energy does not allow to reach high potential, high altitude winds. And conventional wind energy is not mobile and only good at economics of scale, which is unfortunately not very applicable to most of the non-OECD countries, which has a huge potential in terms of investment in future. And so I'll start to talk about airborne wind energy, AV. Okay, let's return back to our problem. So we have a wind speed. It is increasing at higher altitudes, and we have the wind turbine. So what we learned is the tower is a big problem, and so let's drop the tower. But here we have to keep that on air. So we have a gravity, right? So we have to put something to keep it over there. So we can put some balloons or some buoyancy systems and connect it to ground with a tether. This can happen. And there are solutions like that. But for that, still, in terms of system thinking, I think this is not, for me, I'm not so sure it's the best solution in terms of adopting the wind energy. I tend to see the wind atmosphere as a dynamic system, and whatever you put somewhere as a static one, like just stays over there all the time, is something like that. So this is a dynamic system. It tries to move, but you have to come up with a puzzle to fit in that dynamic system in the best way. So I generally like to watch nature. I always try to get inspired by nature in my designs and all my work. So it looks like the tree. The current these static solutions looks like a tree. But what we should do, we should be a bird. We should be, I believe bird is much better at adapting to dynamic systems such as wind. So we should think about more dynamically in today's technology, high technology, and we can do it. So this is the main motivation. So this is the idea actually using the kites or airborne wind energy by Lloyd in 1980s. So this is what happens. On the left side, you see a wind turbine. And the only important thing is the 30% from the tip, which has a higher speed than the wind turbine, provides almost 50% of all energy. So let's take only this part, only that part, and make it as an aircraft, as a glider, as you see on the right-hand side, and let it flow through the crosswind and transfer the electricity or transfer the mechanical energy, as I'm going to mention in the following slides. So this is the idea. So I'll have to give our final aerodynamics 2 course. Okay, so so this is the wing. This is the typical aircraft wing. It's aerodynamic shape. How we have the lift is a higher pressure and low pressure difference between the top chord and lower chord of the wing, and the difference gives us the lift. And there is a drag. If you go through a fluid, it has a drag, and it has different forms of drag, but it means that whenever you want to go through a fluid, there will be a drag. There will be a resistance towards your motion. And lift is, don't get into the details, but I can give you this. It is the square root of the velocity difference between the air and the wind. This is important, and the wing. This is important because it is not the wind speed. It is the relative speed between the wind and the wing. And we have a lift coefficient which determines how aerodynamic your system, and also we can say the same thing for the drag coefficient. And you can play with the CL and CD based on the angle of attacks. This is what happens once you fly with aircraft. The ailerons, for example, in 350, so it is used to change the angle of attack and roll the aircraft. And it changes the CL and CD. So, yeah, this is the end of the course. This was the final. Okay, I'll try to show you two animations, two methods that we learned, which is drag mode and lift mode. I hope you like my animations. I spent like 1 hour for that. So on the left side, we have air again. It is in the drag mode. So what happens is this. So the aircraft moves along a circular pattern, and it is moving through the crosswind. And it has a wind turbine attached on it, and it creates the energy. It has all the generators, etc. on the aircraft. It creates the energy, and it transmits the energy to the ground. So this is one way. So it is called drag mode because the drag rotates the turbine during the flight. And remember, right now the wind is not the wind speed, but the relative wind speed between the aircraft and the wind. So we expect it would be much, much higher than the original wind speed there. And for ground again. So this is something, you don't have anything on the aircraft. So aircraft make 8 motion, and the lift keeps it up and up and up, and you rotate and you play with the CL and CD, and you come to the original state. So this is a loop. But what you do is you transfer the mechanical energy to the basement, which is the tethers here, the tethers which also controls the aircraft. And this mechanical energy is converted to an electric energy on the ground. So this is, we call it real out state, and the lift dominates. And while it goes down, it is controlled stall, which is the reduced lift, and tether force dominates. So it is this reciprocating motion going up and down based on this ideal loop, and this is what happens. And the energy generation profile is something like that. During the reel out, which means for the air gun, it is going up by the lift. So in the reel out, you have a positive power, but for reeling in, that you have to call it back or control the aircraft to have to reduce the lift. And so it is the reeling state. So you have to exert more power. So you have a negative power. But eventually, the net energy is positive. And if you have more complicated patterns, it is something like that. If you have a smaller 8 patterns, which has going lift and stall in the here, if you follow my cursor, you see there are smaller loops here, and you have a bigger loop here, which is the big one going down, and these are the smaller 8 motions. So, but at the end, you have a positive wind power. So let's look at the wind capacity. This shows a wind capacity per 1 meter squared. Per 1 meter squared, how much energy you can get. And let's look at the solar powers on the bottom. So it is 1.3 kilowatts. It is actually the radiation coming to surface, but the capacity factor is 20%. So this is your efficiency, and this is actually much smaller. For conventional wind turbines, it is less than 1 kilowatt. For the wind energy, the potential, the theoretical one is 40 kilowatts, but one of the university teams has reached 6 kilowatt per meter square recently, and the capacity factor is 60%. So there's a huge power capacity per meter square. And installation cost. As you expect, we don't have any tower here, and we don't have big components, so it is very cost effective in terms of material and also installation cost. It is only $2, and it can be reduced, and it is getting reduced and reduced until $1 per watt. This is the installation cost. For solar power, it is 3.8, and it is going to 2 right now in today's values. The conventional wind turbines is about $6 to $4 per watt. So it is also cost effective too. And in terms of manufacturing transportation, this is one of the main value deliverable in this idea. It is very small. It only requires 10 to 15% of material used for one of the wind turbines. And sorry. So as you see on the right, you have just a basement which controls the tether and controls the kite, and you have a kite, and which can be a flexible one, which can be a lightweight one. But of course there are some challenges for the AV. Of course, this is one of the big challenges for this technology is control and reliability, as we expect. So you have to control the kite and keep it there all the time. And this was one of the reasons why Lloyd didn't pursue that one when he first proposed, because in 1980s it wasn't so possible. But with today's high-speed computers, machine learning algorithms, or like fuzzy logic algorithms, there are teams who successfully control the kite. And here the thing is, the kite is moving through a stochastic system, which is sometimes quite turbulent. And you have to reach the high wind potential, and you have to go sometimes higher altitudes to find the higher wind speed. And meanwhile, you have to keep it there all the time. You don't let it go down. And so these are the reliability and control system. These two are one of the most important challenges. But right now, there are very, very promising results in terms of these, and there are companies, as I'm going to show, working on this technology. And the second one is actually related to reliability and the robustness of the system. It is the launching and the landing of the kites. So this is a picture from an Lindenberg kite on the Rumeria River in German expedition. So you see people try to launch the kite. So how can we launch a kite and land it safely, especially if you want to deliver to non-developing countries, developing countries. So it has to be robust, it has to be easy to use, and easy to launch and easy to land, and have to be reliable and safe all the time. And another challenge of this technology is application in farms. As you expect, these are tethers and they are free to move. So sometimes as you're moving through the crosswinds, the angle between the ground and the tether is as low as 30 degrees or 20 degrees. So you need to have a very large free space around the kite system that the tether shouldn't entangle with any obstacles. This can be a building, or this can be another kite. So there are such obstacles in terms of using in farms. But of course there are some solutions for that, and it can be controlled, or you have some smart ideas in that one. So there are solutions for each three big challenges for the EVA technology. And right now, the number of institutions taking place, and more people getting on board. And as you see, it just boosted up after 2009, 10, and right now on the right-hand side, down figure, you see like many, almost 50 institutions, including universities and countries and companies are working on this technology, which is quite promising and which can be really disruptive in terms of wind energy and could be a very good compatible solution to the current solar system, solar energy. And unfortunately, it doesn't have MIT here in this figure. But here, we are 5 students. We are working on this technology. And Carlos, my friend, he has an energy background. He's a mechanical engineer, and he is also pursuing another master's degree in mechanical engineering at MIT. I'm Burak. I introduced myself at the beginning. Jack is also in our team. He's a mechanical engineer. He's an operations guy. And right now he's pursuing a PhD in mechanical engineering department at MIT. Nan is our electronics and computer science guy. He is right now also pursuing another degree in EECS department at MIT. And Charles is our mechatronic guys, and he's an STM fellow like me. Right now our project is funded by the Clean Energy Prize, where we were one of the finalists recently, and also funded by the MIT Sandbox Innovation Fund program. We plan to have a prototype shortly in 6 weeks and start to work on it. So for the final takeaways, after the whole level 0 to level 3 for level 4, the EV promises outstanding mobility, cost and scalability to OECD countries, but especially non-OECD countries. And EV technology has challenges that are being solved right now, and there is a huge amount of effort to solve everything, and majority of the problems are solved in 2017. So thank you very much. This is the end of my presentation. If you have any questions, please ask, and I put my contact here, and you can email me whenever you want. Thank you.
Thank you. So time for Q&A, and sorry, got it. Sorry about that, folks. If you have any questions that you would like to ask Burak, please type them directly into the chat. We have about 10 minutes or so for Q&A, and we invite your questions. We have a first question from Vivek Ranka, who says, you have considered using the eddy currents generated around the skyscrapers, or have you considered using the eddy currents generated around the skyscrapers? You would reduce the cost on big windmills.
Yeah, it's a very good idea. Right now, we are considering those solutions. One thing that I didn't show here is actually the regulations in terms of the altitudes. FAA have some regulations in terms of reaching the altitudes, even though it can be a kite or it can be an aircraft or flexible or rigid wing kite, doesn't matter. So right now we are trying to understand the regulations, but there is a huge potential for the buildings, and we plan to talk to buildings around Boston and Massachusetts for that. Yeah, it's a very good idea. Right now we are considering it. Yeah, thank you very much for this.
Great, thank you. We have a couple of more questions. Just a reminder, folks, if you would like to raise a question, please type it directly into the chat. The next question is from David Kleinschmidt, who asks, what is this structure? What is the structure that connects the kit to the ground?
Yeah. Okay. So it is the flexible tethers, but high strength tethers, low weight, high strength tethers connecting the ground. There is one thing here that we should consider is this. In our current design, we have 2 tethers, but adding more tethers means more drag and more weight. Actually, sorry, a drag and the weight is a very big factor in the efficiency of the kite system. So right now it is 2 tethers connecting to the ground, and which is controlled by electric motors, and but there are solutions that only connects the kite to the ground with a single tether, and there are two tethers at the end of the kite because you have to roll, yaw, other maneuvers to control the lift and the drag coefficients of the kite to control it on the air. So eventually you need to have at least two tethers on the kite. But how many tethers going to ground should be as minimum as possible, and it should be one. There are solutions. For example, I know the Delft Technology University, they are controlling the kite with two tethers, but they have a device just below the kite, and after that device there is a single tether going from that device to ground, and this device is also flying together with the kite, and this device is controlling these two tethers on the kite. Yeah, so it is the tether and more than one, but should be as minimum as possible.
Great, thank you. The next question is from Jonathan Allen, who comments, it looks to me like a giant box kite might be advantageous. Your thoughts?
Yes, exactly. There is a one, so for box kites, the drag is the drag is a very important issue here. There are teams who are working on box kites. Actually, it is up to your solution. And for us, we are focusing on very, very low cost solution. And we try to minimize the complexity of the system, because eventually we aim to send our kites to developing countries. And we somehow try to use the off-shelf kites instead of coming up some customized kites. And second thing is, important thing in designing a kite is the durability. So right now, in most of the kites, people use it for fun, but here we will use it for hours and hours, and in the night and day, under the rain, and it should work there. So we should come up with a less complex, having a design with a less complexity, but a durable one too. Yeah, these are the consideration, but of course, yeah, box is a good solution too, and there are teams are working on it.
Great, thank you. We have time for a few more questions if anybody would like to type something into the chat. In the meantime, I will let you know or remind you that you will all be getting a link to the recording and the slides in about a week. And it will also contain information on our next webinar, which will be on May 8th. That's a Monday, same time. And it will be presented by two SDM alums and a key person at the Chilean Ministry of Energy. And the topic is best practices for water use at thermoelectric facilities in Chile and Latin America. Again, you'll get info on this when I send you the link to the recording and the slides. So it looks like there are no more questions. So with that, I would like to thank Burak, Dr. Gozluklu, and our tech guru, and Eric Ferris, and our multimedia expert, Dave Schultz, and all of you for joining us. Have a wonderful day.
Thank you.